In this video, I'm going to do some examples of substitution. And so we're looking at chapter 44, substitution. Substitution is a technique of integration. When you get to Calculus 2, you're going to learn lots of different techniques of integration. In Calculus 1, you basically learn two. One is substitution, and the other is just what I call eyeballing it. You just know what the antiderivative is. So we don't do a whole lot with techniques of integration in Calculus 1. You'll learn more in Calculus 2. And so we have this integral, and this is going to be a very nice, straightforward substitution. So we have this polynomial to the fourth power, and if you take the derivative of this fifth degree polynomial, you have 5x to the fourth plus 6x squared, which is what this is. This is our clue that we want to use substitution. If you see a term in here whose derivative or a rational multiple of a derivative is also present, then that is a good indication that you want to use substitution. So we'll make our substitution. We'll set u equal to x to the fifth plus 2x cubed plus 1. And now we'll look at the differential du. Remember back in the chapter on differentials, du is going to be this derivative times dx. So du is 5x to the fourth plus 6x squared times dx. And now we make our substitution. I did not rewrite the integral here to save board space, but this integral in terms of x is now equal to this integral in terms of u. And so this is just the integral of u to the fourth du. This is u to the fourth, and the du is 5x to the fourth plus 6x squared dx. So this term times dx is du. U to the fourth du is just a polynomial. We calculate the antiderivative. We have 1/5 u to the fifth plus c. Then we have to substitute back, because we're trying to find an antiderivative of a function in terms of x. We cannot give our answer in terms of u. If we could simply say, okay, let's just make it w. And what is w? Well, w is the variable that makes the answer right. So we can't do that. We've been given an integral in terms of x, so we have to give an answer in terms of x. So we substitute back now. So we have u to the fifth, and u is x to the fifth plus 2x cubed plus 1. So this is our u to the fifth, plus our arbitrary constant because it's an indefinite integral. Now if we look at part B, there are two differences between part A and part B. Difference one is it's a definite integral now instead of an indefinite integral. That means our answer is going to be a number and not a function, or a class of functions. The other difference is the substitution is nice, but it isn't quite as nice as it is in part A. We have a third degree polynomial right here. The derivative of a third degree polynomial is a second degree polynomial. So if you take the derivative of x cubed plus 4x plus 4, that derivative is 3x squared plus 4. That's not quite what we have here. We have 6x squared plus 8, but that is exactly 2 times 3x squared plus 4. So we can use that. So we'll set u equal to the third degree polynomial, and what is du? It's the derivative times dx. So du is 3x squared plus 4 times dx. So this integral that we were given is what? Well, this is the square root of u. 6x squared plus 8 times dx isn't du, it is 2 times du. So when we substitute the variables, this expression becomes 2 square root of u du. But when we have a definite integral, we also substitute the limits of integration. When x is equal to 0, what is u? When x is equal to 0, u is 4. And when x is equal to 1, what is u? It's 9. And so we change our limits of integration as well. So x changes from 0 to 4, and changes from 1 to 9. So we change our limits of integration. When we do this, we don't have to substitute the variables back, because remember, a definite integral is a number. It is the same number, just written a different way. So we'll find an antiderivative of 2 times square root of u, which is 4/3 u to the 3/2. Our limits of integration are 4 to 9. So we substitute 9, we substitute 4, and we subtract. And if we wanted to, we could have substituted back for the x and substituted these variables back for 0, 1, and substituted 0 and 1 back in, and we would have still gotten 76/3. But that's a wasted step. Once we substitute, once we put things in terms of u instead of x, and we substitute our limits of integration, again, we just have the same number written 2 different ways. So I just like to do things in terms of u and not look back.